Welcome back, class. We're going to move on in our unit of similarity. We're going to continue with video number 2, boom, in proving triangles similar. So in the previous video, if you haven't watched it yet, we went over the angle-angle postulate and we did some proven stuff, right? So hopefully we're overcoming some proofs. So today we're going to learn about some more similarity postulates and we'll get into verifying triangle similarity. So how's that going to work? Well, of course, we're going to start with notes. In the last video, hopefully you recall, we established angle-angle similarity. And in this video, we're going to talk about a couple other ways that we can prove similarity. So the first note is called side-angle-side similarity. Now the way this works is that if an angle of one triangle is congruent to an angle of a second triangle, we've established congruent angles, and that the sides that are including, okay, the two including sides, okay, so we have AB and QR and AC and QS. Okay, so if we talk about those sides, if they are proportional, okay, if the sides are proportional, but the included angle is congruent, then we have similar triangles. So we have to talk about proportional for sides, which we know from the previous lessons, and congruence for angles, which again we know from previous lessons. So we can establish a proportion. We can establish AB to QR, being equal to AC to QS, AC to QS. That means they are proportional. So if we can establish proportionality and the included congruent angle, we have similar triangles, right? So that's an important note. And another note. Side-side-side similarity. Okay, so there's the three ways that we can talk about similarity. Angle-angle, side-angle-side similarity, and side-side-side similarity. Now, how does this work? So this is working if the corresponding sides of two triangles are proportional, then they are similar. So it's like we're starting with the very beginning definition we talked about for triangles being similar, then the sides are proportional. Okay, so when we talked about similar polygons, we knew about proportionality. That's what this similarity theorem is about. So again, we're talking about proportionality, and it's talking about corresponding. Corresponding, such a huge word. That means AB corresponding to QR. That means AC corresponding to QS. And then that means BC corresponding to RS. And if all of those proportional statements are true, then we have similar triangles. So if AB to QR is equal to AC to QS is equal to BC to RS, all three sides proportional, boom, similar triangles. Okay? Okay. Mr. Katz, I don't get it. Let's do some work. Let's do work. So, here's an example. Are the triangles similar? If so, write a similarity statement for the triangles. Now, in the previous video, I talked about the importance of correspondence. Here it goes. So, when it comes to correspondence, it's going to be pretty challenging to make sure we see what corresponds to what. So, if I look at triangle, let's say UST, and I redraw triangle UST, and I look at this triangle, I'm not going to name it yet because I don't know what corresponds with what. I'm just going to draw a bigger triangle because clearly whatever we call this triangle, it looks bigger. And not only does it look bigger, the sides are labeled bigger. So I want to draw it in the same direction so I can compare the corresponding things. Okay, so how is this going to work? I know this triangle is UST, and I know the distances are 10, 6, and 8. Now, 10, of course, of the three is the longest, so I'll label that with a 1. 8 is the second longest, I'll label that with a 2. And 6 is the shortest, I'll label that with a 3. So, of the other triangle, the bigger triangle, which side is the longest? 15 is the longest. So I know in my other triangle, if 10 is here, the longest side is here, then in the corresponding triangle, 15 will be here. In my second triangle, 12 is the second longest. So in my second triangle, if 8 is here, then 12 will be here. And then lastly, if 6 is here, then 9 will be here. Okay, so again, I didn't know the name of this triangle. I don't know what triangle. If I'm calling this UST, right, if I'm calling this triangle UST, what will correspond? And now I know, because look at 15 and 9 are here, right? 15 and 9 are here. Angle X is between 15 and 9, right? So between 15 and 9, now I know up here is angle X. Angle V is between 9 and 12. So angle V is between 9 and 12. Angle V is here. And then angle W is out here. And so now I know my corresponding things. Okay, so my triangle, if this is UST, is going to be WXV. Correspondence is huge. Now, once we have correspondence, can we talk about similarity? Can we talk about similarity? And the answer is, well, I hope so, because of what we had just learned. If the corresponding sides are proportional, that means if I have 10 to 15, right? 10 and 15 correspond. Is that going to equal 8 to 12? Okay, so 8 in the small one, 12 in the bigger one. And is that going to equal 6 to 9? So hopefully you understand what just happened. We're going to see if this is true. If this is true, if we have a true proportion, then we have similar triangles. So let's figure it out. Let's simplify each ratio and see what we get. 10 to 15 are both divisible by 5. That leaves us 2 to 3. 8 to 12 are both divisible by 4. That leaves us 2 to 3. So far, so good. It's looking good. 6 and 9 are both divisible by 3. That leaves us 2 to 3. Winner, winner, chicken dinner. We have similar triangles. So when it says write a similarity statement, I want to make sure that you are having the triangle labeled in the corresponding manner. Angle U corresponding to angle W, angle S corresponding to angle X, and angle T corresponding to angle V. So we have to be super duper careful, making sure that we are labeling it correctly. Okay? Okay. Next question. Are these two triangles similar? Yes, no, maybe so. So this one we'll see how we're going. Now again, what I want to do is I want to create my two separate triangles to make sure I know what I'm looking at. Okay, so I have my first triangle, and I will call this one KLP. KLP. And I will call my second one, which seems to be bigger. In the bigger triangle, we will have KMN. KMN. All right, so at least I know how the triangles will be labeled. Okay, so hopefully we know how the triangles will be labeled. So now what we have to do is let's take a look at what we know. In triangle KLP, I have K to L, K to L. I know that distance is 8. Okay. In K to P is 12. I know that. So what does that tell me in triangle KMN? Well, how far is it then from K to M? Well, look, from K to M is 8 and 2. So 8 and 2 is 10. So the total here is 10. Okay, so that we have to establish. And if that's the case, then what is going to be from K to N? So K to P is 12. P to N is 3. 12 and 3, 15. So from K to N is 15. So now we have a problem, right? Well, darn it. I only have two sides. How am I going to prove similarity if I only have two sides? Don't I need all three sides to be proportional? And then the answer to that is, dude, did you even watch the first part of this video? Because we have angle side similarity as well. That means if the two sides are proportional, can we establish that the included angle is congruent? Okay, so can we conclude that the included angle is congruent? And of course, yes, because angle K is angle K. Reflexive property. Okay, so remember, reflexive property of congruence. We know that angle K is congruent to angle K. So all we have to prove is proportionality of corresponding sides. Okay, so can we say that? Can we say that 8 to 10 are corresponding sides? Can we say that 8 to 10 is equal to 12 to 15. Can we say that? Ooh, wrong color. 12 to 15. So that's the question. Is that a true statement? Okay. So let's figure out. Let's simplify each ratio. Okay, so 8 to 10, both are divisible by 2. That leaves us 4 to 5. And 12 to 15, both are divisible by 3. That leaves us 4 to 5. Winner, winner, chicken dinner. They are proportional. We do have side angle side similarity. The included angle is congruent. The sides are proportional. We do have congruence. All we have to do is write our congruency statement. If I call this triangle KLP, I have to say that it is similar to triangle KMN, and then we are good to go. Okay, so that's how these two new similarity statements come into play. So hopefully that was doable. If not, rewind. Next example. Are these two triangles congruent? If so, write a similarity statement. So here we go again in different shapes. So what I want to do is rewrite them so that at least they're in the same direction. Personal preference, I like, as much as I say don't let gravity mess with you, all right, some cases gravity messes with me. I want to make sure that my triangles are easy for me. Right? If you're totally cool, if you're like got artistic brain and you're cool with upside down triangles, dude, knock yourself out. Ain't nothing wrong with that. But this is what I know. If I'm going to write this triangle over again, I'm going to keep sure I know my side lengths. I got 9 here, fine. 6 here and 6 here, fine. So between 6 and 9 is A, and between 6 and 9 is B. So let's call it A, B, and then C is at the top, right? So as long as I'm rewriting stuff, I'm okay. In the big triangle, I know 12 is my base, and 8 are my sides, and then I can just leave that. That's E, G, F. So the only question now is, are these two triangles similar? Do we have proportionality with our side lengths? So is 6 to 8 equal to 6 to 8? Right? 6 to 8 equal to 6 to 8 equal to 9 to 12. If that's the case, we have similar triangles. Okay, so notice how I like to draw the base down. You didn't have to. You don't have to do that. You don't have to do this as long as you know what you're doing. Just personally, I need that. Anyhow, 6 to 8 both divisible by 2. That leaves us 3 to 4 equaling 3 to 4 equaling 9 to 12 both divisible by 3. Hey, 3 to 4. Winner. So yes, these are congruent, but we have to write the similarity statement. What is congruent to what? So we have to make sure we're labeling our triangles correctly. Triangle ACB would be congruent to triangle EGF in my case. And would it matter if those were backwards? No, because they're isosceles, but whatever, not the point. So hopefully you learned a little bit more about verifying triangle similarity. And that is it for this video. Come back for part 3, and we're going to talk about finding lengths in similar triangles. I will see y'all later.